Why is the gradient grad f at P, this vector, why is it orthogonal to the contour at P? Okay, so somewhere in our input space is a point P, and there is a vector there called the gradient of f. Well, this would be a map, and then this would be a specific vector at the point P. So grad f evaluated at P is a vector. Then the vector, every vector, it determines a line. A line through P. It determines a normal line. In other words, this line has 90 degrees. Okay, and that line, so now, that line includes all vectors v with v dot that vector equals 0. So this vector v has dot product 0 with the gradient. This vector v has dot product 0 with the gradient. And that's what this linear equation of the line means. Discovery. The derivative of f at P in direction v is equal to that dot product. This is what we saw was amazingly the case, that this one-row Jacobian, we take v and we make a linear combination of its columns. In the case where f has one output value, we get one row, and that one row we can interpret as the gradient, and then the derivative is the dot product. Okay. Great, we're almost there. Recall our linear approximation formula. The function value at f plus v is basically f of p, at p plus v is basically f of p plus the derivative in direction v. Okay, but if v is in the orthogonal line determined by the gradient as its normal vector, as the normal vector of the line, then, df p of v is 0. But then, f of p plus v is equal to f of p plus 0, which means the function value stays the same. Stays the same. Well, to linear approximation. Okay, and remember, the places where the function value actually stays the same, those are contours. Those are level sets of the function. Those are preimages of the function. And so that is why we see that there is some contour, like f of p is some number, some real number, and we can look at all the points who take the value f of p. And we see now that this contour of all inputs with value f of p, that contour has to be orthogonal. Well, what does that mean? I mean, this is a curve. our original function f might be nonlinear, you can take this as the definition of being orthogonal to a curve. Curves are curvy, so what direction is orthogonal? Well, at a point, we look at the linear approximation to the curve, and that will be a line that is best approximating the curve. And we see that the gradient is 90 degrees to that line. Okay, we didn't know that at first, we just knew that gradient was a vector. Well, of course, a vector determines a normal line, and that line includes all the vectors that have dot product 0. That's the definition of the equation of that linear line. Then we discovered that that dot product was actually the derivative. We looked at our linear approximation formula and saw that if v is orthogonal, if v is like that or v is like this, well then the dot product is 0, and so this piece is 0. But that means the function value stays the same, which means to linear approximation, such v stay on the contour. Well, mostly. You can see it's already left the contour, but only by a little bit nearby. Okay, that's all.